Hello there, we're going to take a look at continuity in Chapter 1, that's Section 6. Now this is going to be a little bit shorter than what is in the book. I'm going to take what I think you need to know and leave out some of the exotic stuff that you will only need to know really, I think, if you were taking Calculus 1. So be aware if you share this with someone who's taking Calculus 1, this isn't the whole deal about continuity. It might not help them a whole lot, but it might give them a kickstart, who knows. So some of these things I'm going to talk about, and other things I won't. So first thing I need to do is get straight here. First thing I need to do in each one of these is tell it to use the pen. So we've got the pen, and since red looks pretty good here, notice that? So we're going to stick with red. And in this, we're going to take a look at determine the continuity. The continuity on a closed interval, in other words, only from like 6 to 19 or something like that. We're not going to bother with the greatest integer function. There's some interesting things there in real life problems, but we're not going to bother. And also this last one, compound interest. I like compound interest, but it refers to continuity. We'll leave it out. We'll get back to compound interest in a different way, and I think it's Chapter 4 when we talk about exponents. So number 1 and number 2 in particular. Other than that, we're going to move on. So continuity in general, sort of a ballpark look at, or an airplane view of it. Okay, so in mathematics, we use the term continuous to mean that there's no breaks anywhere. Okay, so when we talk about being continuous, we also are interested in where it's continuous. And in this case, we're talking about for values. That's what the x represents, different values. It's a variable. And this c represents a particular constant. So for example, we might be talking about continuity at x equals 6, or x equals negative 19.3, whatever. You get the idea. That means when you go from less than 6 over here to greater than 6, there's no gap that you have to jump if you're graphing the equation with your pen or pencil. That's all it is. It's unbroken at c, and c represents some number. C they use because it represents the word constant. So you can remember it that way. If you were in another country, they might use k, like, maybe they spell it like this. They might use k. Sometimes k is used. The thing is, it's unbroken. You can get from one point to the other while jumping. It has no holes, no gaps, or no jumps and no gaps. Now, it's pretty simple, but strange thing is it took a long time for mathematicians to actually narrow that down with a precise definition. It wasn't until the early 1800s that really happened. If you're interested, you could probably get all you need to know off Wikipedia. So here's a graph you can look at. Now what I would suggest, first of all, was like, okay, so imagine you're taking a trip along the Cartesian coordinate system. And to take that trip, you follow the graph. So you pick up the graph somewhere around here, and you follow it as much as you can. But notice what happens right here. There's a gap. So if you were going along this curve, you'd have to jump over this to get to the rest of the curve. When you get down here to this point, you can't just go from there to the next one without making another jump. So I hope you're a good long jumper or a high jumper, because you're going to have to jump from here all the way down to here before you can continue on this curve. And over here, now this is really even more strange perhaps. So you get here and you see, uh-oh, I've got another gap there. It's a discontinuity, to be exact. But if you want to be at C3, whatever that number is, you're going to have to jump sideways, get down here, and then you're going to have to jump the other sideways to get back on the main path. Those are examples of what they mean by a function being not continuous. So if we look at that picture that I've reproduced on the right, you can see that, first of all, at C1, remember C1 is over here, so we're talking about graph-wise, we're talking about up here. It's defined. That means that to be continuous, it's going to have some function value at C1. Here it doesn't have one. If you ask for the y value, for example, at this number, say this is 6, and you say, what's the function value, or what's the y value at x equals 6? In this case, there is no answer. It's not defined. And that's what the first note up here is saying. At every point when you go from left to right, every x you pick has a y that actually gets matched up with it. In part 2 over here, this one says at x equals C2, so let's say C2 is 10, for example. At C2, the limit doesn't exist. We've talked a little bit in the previous video about existence, or limits rather. That means that from this side, it approaches a certain place. From this side, it approaches a certain place. But those two have to match. They don't match. From the left side, it's getting close to that dot right there, that y value. From this side, going from the right to the left, it's actually getting close to that point. That's not consistent, which also means for us, it's not continuous. Part 3 over here. What does this say? This says that at C3, and let's say this is number 17 for C3. C3 is 17. This says that the function value at C3 is not the same as the limit. What does that mean? Let's get back on our graph and take a trip. If I'm coming on the curve from this side, what am I getting close to? I'm getting close to this y value. If I come from this side, I'm getting close to that y value. Now that sounds good, except for the fact that it doesn't even exist there. The actual y value for 17 is down here. That would be another example where we would not have continuity, because from one side it approaches one thing, from the other side it approaches the same thing, but it doesn't hit at that limit. It actually gets bounced down here and then jump back up. Hope you get the idea there. Maybe some examples in the book will help. So here's a summary of those. First of all, remember, C is a number. And what this means is that if you pick an X, there's a Y that's matched along with it. Every x you pick in the domain has a y that gets matched up with it. That's what definition means. That's number one. Number two says when you get to C, when x approaches C, the closer it gets, the closer it comes to a particular value, whether you're coming from the right or you're coming from the left. There is a limit from both sides. But that's not enough. You have a third condition. You have a limit from the left side, a limit from the right side. They exist, but are they the same? And are they equal to the function value or the y value where you have an x equals c? You need all three of those to actually have continuity. The good news, some really good news. Typically, we're using polynomial functions. And if we're using polynomial functions, sort of like x squared plus 17x minus 32. Those are all, you've got each one of these powers of x is an integer, a positive integer, and you go from usually from left to right like this. It looks really, excuse the expression, but normal or typical for a function. Where you get something exotic, now this one is continuous. This is a polynomial function. If you had something like, I'm going to just change one thing. Suppose this was x to 1.8 power instead. No matter what is out here, it's not a function, because these have to be integer values for the exponents. This is not a polynomial, which means it might or might not be continuous. It has to be one of these nice polynomials, and then you're guaranteed continuity. For number two up here, which I've half obliterated, for the rational functions, what does rational mean? In common terms, we're talking about a fraction. So you might have a function like f of x equals x plus 5 over x squared plus 7x minus 2. It just means you've got a polynomial on the top, a polynomial on the bottom. That's what a rational function is. And if you go to rational function, now this is a little bit clever if you're not careful. It's continuous at every number, and then these last three words are the trip-up point in the domain. That means any legal value of x is going to give you a rational function that's continuous around it. An example over here. Let's say we have a function called g of x, and let's just say this is x minus 3 over, and I'm going to factor this out to make this easy, x minus 2 and x minus 6. Now, the top is obviously a polynomial function. The bottom, if you expand this, you get x squared minus 8x plus 12. That's a polynomial. So this is a rational function. However, the catch is it's only continuous for elements of its domain. And the domain depends on what you see in the denominator. Now, the reason I factored this or put it in factored form is that there are two catches to this whole thing. G of x exists. In other words, that y value exists almost all the time. But imagine what happens when x equals 2. If I put a 2 in here, we've got the denominator is saying 0 times something else, -8 to be exact. It makes the denominator 0, which means g of x won't exist at x equals 2. So this rational function will not be continuous here because this is not in the domain of g. It's not in the domain of g. And also, if you take a look at the second part in the denominator, you have x minus 6. You can easily figure, I think, we've got another small problem on our hands. X equals 6. We can't use 6. That's not part of the domain for g of x. So this particular function, g, the one we're looking at right here, here's a little eyeball for you. We're taking a look at g of x. It's going to be continuous everywhere except where x equals 2 or x equals 6. Everywhere else, it's nice and smooth. Now, before we go on to the next slide, I want to suggest something to you. You should have a graphing calculator. So my suggestion to you is hit the pause button and graph that rational function on your calculator. You can leave it like this, or you can expand it like I mentioned earlier. We have x minus 3 on the top and x squared minus 8x plus 12 on the bottom. Graph that. Look at what happens as you're going from left to right. Everything is fine from negative infinity until you get close to 2. And then all of a sudden, when you get close to 2, there's a big jump. I'll let you figure out what that looks like. When you get on the other side of 2 and you've made that transition where it's not continuous, things look fine from 2 to almost 6. It's continuous in there because all those numbers are in the domain. Once you get past the 6 where it's discontinuous, things smooth out again and everything is perfect. It's continuous after 6. Okay, so I hope you get an idea. All polynomial functions are continuous everywhere. Rational functions are continuous almost all the time. If you look at the denominator, figure out where is that rational function not continuous. That's what you need to know about continuity. Now let's take a look at a couple of functions, or 3 in particular. First of all, look at part A. We've got a function. Let's call it f. It's x squared minus 2x plus 3. You can tell right away each of these exponents for the x's are integers, positive integers, excuse me. 2 there, and of course the 1 there is understood, and we don't have to worry about that because it's just a constant. We only need to be concerned about the exponents of the variable. Now if, for example, this were 3 to the 7.256, we don't care. Regardless of what that is, regardless of what the exponent might be, we don't care because it's a constant. That's all that matters. It's only the exponents of the variables that have to be positive integers. In fact, some of you might want to tune this out, but this last part where we had the 3, another way of writing this f of x, by the way, is x squared, there's a 2, positive integer, minus 2x, a positive 1, and actually, we can write this one if we're really particular. You could write this as 3 times x to the 0. But any number to the 0 power, any non-zero number to the 0 power is 1. So it's 3 times 1, it's just 2. It's a fancy way of writing the number 3. That's all it is. And in this case, it's a 0, as long as, I should have said, as long as the exponents are non-negative integers, because 0 is okay. All right, so this is a polynomial, so definitely it gets the big C for continuous. Part B, take a look at that. We've got a 3, that's a non-negative integer. We've got a 1 here, that's a non-negative integer, nothing else. So this also gets the big C of approval for continuity. And part C, another function defined using the letter F. We've got x to the fourth, x to the second, and for those of you who insist, we'll make this x to 0. We've still got all of these exponents for the x's being non-negative integers. So, another C for continuity. All right, if you have any questions, write them down, bring them to class, bring some examples that you're wondering, I think this is a gray area. How does this work? Well, bring it in. That could be your J1Q for Monday or Tuesday or whenever we talk about continuity, even in brief. So here are pictures of those three functions. If we snuck back a second, there are your three functions, and there are the graphs of those very same functions. You can see if you look at it. Now on the first one, this was A. You can see that down here, but I'm emphasizing that. You can see that if you start here and you're traveling along that graph, you never have to lift your pencil or pen until you decide you're tired and you want to stop. No problem. Part B, same thing. Start over here anywhere you like, even if it's further down. You want to start here. Travel along that graph. You never have to lift your pencil. Of course, there's the reason it's continuous. And the third one, a little bit of some people used to call this sort of a dipsy doodle. That's way back before my time even, but it does a weird flip here in the middle, makes it more interesting. But the point is, you start at one side, travel along that function, we never have to lift our pencil. So it also is continuous. Next. So this doesn't say a whole lot except polynomial functions are really important. Those are the ones we're going to be using primarily, but occasionally they're rational functions and they can be a little bit more interesting. Just remember, when you have a rational function, take a look at the denominator and determine when that denominator might be 0, because you can't divide by 0. And just a quick reminder, for example, if you've got, let's just say an x here and a y there. If you put this in the calculator, as long as this in the denominator is not 0, everything's fine. Just ask your calculator. It'll do any division at all as long as you're not dividing by 0. Got that? All right, let's keep on moving. And we'll take a look at these. Recognize these? Rational functions. Why are they called rational? They're called rational. First of all, it starts off the first 5 letters of ratio, and translated that means fraction. And in addition, you might remember that not only does it have a fraction, but there's x or y or z somewhere in the denominator. If the denominator has only a number, you don't have a rational fraction. You don't have a rational function. Everything is fine, and you still got a polynomial most likely. So, take a look at the first one. Maybe take a pause. Fool around with 1 over x. Graph it in your calculator or look at that denominator real hard. What is the deal with the continuity of this function? When you come up with something, write down a little scribble for part A. What do you think about the continuity of that function? And then slip down here to B. What's your comment about part B? I won't ask you to initial it. It's all up to you and this video. And go to part C, take a look at this function, see what you think might be true of this one. I would challenge you to take a look at it mentally and see what you think, and then graph it on your graphing calculator, your trusty graphing calculator, and see what you find when you see the picture actually itself. So, each one of these is a rational function, right? We've got x's in the denominator. So it's continuous at every number in its domain, and you know now that this is the catch in the domain. So for each one of those, you want to look at it and say, well, which places isn't it defined? The simple one is up here. You look at what's in the denominator, and you say, well, this is simple. I don't want that x to be 0. So very simply, you take the denominator, which is only x in this case, set it equal to 0, and that tells you right away there's no work here. This is a place where it's not continuous. In the second one, you look at the denominator again. Set that equal to 0. Now you don't know immediately, but solve that for x equals 1. This is where that rational function is not continuous. It's as simple as that, really. The third one is sort of a trick question. So you look at the x squared plus 1 and you ask the big question, when is it 0? Okay? Well, one thing we could do, we could solve that for x squared. And the x squared equals -1. And if we don't go too much further, we could ask ourselves, okay, what's the deal with x? If I square a number, can I ever get a -1? Absolutely not. When you square any real number, you get a positive number or 0. You definitely don't get a negative number. So there's no x that's going to make things continuous. This will be a nice continuous function, actually. So here's 1 over x. I hope you actually tried that for yourself. Notice as it approaches that nasty x equals 0 down here, as it gets closer to x equals 0, it goes a little bit nuts. It's not going to connect to the right side. You've got a discontinuity between here. In other words, if you're graphing this, you're going to have to make a big jump to go up here and continue graphing your function. Excuse me. X equals 0 is where it's not continuous. Or another way of putting that is, it's continuous from -infinity to 0. Jump over the 0. It's continuous from 0 to positive infinity. Second function, or part B, there's your graph, and you can see as your eyes travel from left to right along that line, a curve in some cases, that everything is fine until you get to x equals 1. Remember, we found that out. X equals 1 is where it's discontinuous, because to get from the left side to the right side, you have to jump over x equals 1, because it's not defined as a function for x equals 1. That's a discontinuity in one point. And last, part C, the one we had there. And you might, if you were writing that, I would think you would write it as f of x equals 1 over x squared plus 1. You might put in your calculator this way. So I guess someone was trying to do their calculator. But you can see what happens. It does do something interesting with 0. But there's nothing wrong with putting a 0 in for where the x is. If you put a 0 in for the x, which can be done like this, f of 0 means you take the 0, put it in where all the x's are. What do you get? You get 1 over 1, or just 1. So it is defined. And there it is on your graph. Bingo. Well, I hope you've enjoyed our travel through continuity. We're not going to get exotic because we don't need to. Some classes, even maybe the same class, will do it a little bit differently. This is my take on it because I think this is what you need to know. I'll see you again in class, and I'll see you in section 2.1 when we start working on some real more calculus looking things. Until then, you take care and see you again.